So I will get started with the bonding in metals. Now, we are probably, as a society, more familiar with metals than any other kind of chemical substance because we use them all the time for various things, right? Even though they are very familiar, to describe the bonding mechanism is, at least in specific terms, is more difficult than it is for ionic compounds. Because essentially, here's what you have to think about. Metals have the following properties. To some extent or another, they conduct electric current. We use them for wires, right? They also conduct heat. If you have ever left a frying pan on the stove with the heat on and came back in a while and put your hand on the handle, you probably learned that metals conduct heat. But I have to tell you that the extent to which they do that conduction varies with the kind of metal we're talking about. Some metals conduct heat very quickly, like silver, for example, and copper. Other metals, like tungsten, for example, does not conduct as readily at all. And the same thing is true for electrical current. Some metals are very good conductors, meaning that the resistance to the flow of electric current is very low. And that's why we use copper for the wiring in our cars and our homes and so forth, for the most part. When I first moved to Houston and bought a little house, it had aluminum wiring in it. And when I found that out, I was very much concerned because aluminum, although it conducts very well when the surface is clean, forms very readily an oxide coating. And you can't really stop it. If it's exposed to air, it's going to form this oxide coating. So anytime the aluminum is making an electrical contact with something else, then that oxide interferes with the electrical contact. So eventually they got different kinds of contacts for the plugs in the house and so forth. So it's safe to use aluminum wiring now. You don't hear much about it. But at that time, there were lots of fires blamed on it. And when after I'd been living in the house for a while, my wife said, "Feel that?" And she showed me an electrical plug that was too hot to hold your hand on when nothing was plugged into it. So the extent varies widely, and the mechanism that I have to show you to describe the general bonding in metals really doesn't give you a thorough explanation for that. The method we're going to use to describe the bonding in metals is called the Electron Sea Model, and it is 99.9% qualitative. What it says is that in a metallic lattice, for example, a piece of sodium, one describes the bonding as having metal cations that are arranged in a three-dimensional array, and the valence electrons that were released by the formation of the cation here, the one electron that sodium has, for example, is free to move throughout the lattice. And so everything that's yellow on this little thing is negative charge. And it's said to be delocalized negative charge because there's nothing controlling where it stays. Now this is good in accounting for both electrical conductivity and heat conductivity, because if this is a piece of sodium wire, let's say, and you hook up a battery to it, the positive charge and negative charge can cause these electrons to move. And in fact, the conductivity of electricity and heat occurs because electrons are mobile. They can move in the sea of electrons that surround the cations in the metal. The cations are stabilized by this because this sea is a sea of negative charges. And each cation is surrounded by a three-dimensional sort of electron fluid, if you will. You look at it that way. And these electrons can move. So the delocalization allows for electrical conductivity and also heat conductivity. It's also true that the bonding between the delocalized electrons and the cations is non-directional. It's based on Coulomb's law, which only worries about the charges in the distance. And there isn't any force that causes these things to be lined up the way they are in a directional sense. So if you took that piece of sodium and you hit the corner of it with a hammer, it would deform. And typically, we call the behavior of metals whereby if you pound them, they deform, malleability. And if you've ever seen gold leaf, gold metal that's pounded into an exceedingly thin sheet, just a few atoms thick, this illustrates the fact that the bonding in that thin sheet continues in the same way that it was described in a big chunk here, because there isn't anything stopping the atoms from moving into different orientations, if you will. Now, the extent to which the atoms are held together, the force, of course, will depend on how many electrons are in the electron sea. And up to 3 electrons we view as having the atom having the capacity to build up the electron sea, 1 electron, 2 electron per atom, 3 electron per atom. Now, the more electrons there are, and the higher the positive charge of the metal that produced them, the stronger the interaction. So that the melting point of metals and the structural strength of metals, too, depends on how many electrons, according to this model, are delocalized in the electron sea. And as the number goes up from 1 to 2 to 3, the melting point of the metal goes up as well, and the structural strength goes up. By the time we get to iron, for example, we use it for building buildings and building various kinds of things that need strength in the structural members. And iron has a lot more electrons. Well, that's a little bit qualitative as far as an explanation goes, but it is, in fact, essentially true. Would you close your laptop, please? Thank you very much. I have just made a graph that deals with the melting point of group 1A and group 2A elements here. And these are in degrees Celsius, and these are the periods going down the periodic table. So if we look at the group 1A elements, lithium, sodium, potassium, rubidium, cesium, and francium, the melting point is highest for lithium and decreases as you go down the group. The reason for that, as told by the sea of electrons model, is that lithium is a small atom and it creates a small ion, and that 1 electron creates a certain level of Coulombic attraction with that small ion because the electron can get close to it because lithium is small. Sodium is a bit larger. The electrons can't get so close to sodium, and so the Coulombic strength, the Coulombic energy of the system drops, and the melting point falls from, let's say 150 down to 100. And potassium is a larger atom yet, and its melting point gets smaller until cesium melts at about body temperature. Okay? So the size of the atom is responsible for that. If we go to the group 2A elements, where you have 2 electrons per atom in the sea of electrons, the melting point goes up dramatically. Beryllium has a melting point up around 1,300 degrees Celsius. Magnesium drops down. Calcium is a little higher than magnesium. You might think it would be continuously getting smaller. They don't change radically as you go down. But you can see that 2 electrons in the sea of electron makes for a higher melting point in every case than 1 electron. So the only other thing I haven't mentioned about metals is something called ductility. Does anybody know what ductility is? He says it's the ability to draw into wires. And that is exactly correct. Many metals, like copper and silver, have the ability to form extended linear structures, which we, of course, call wires. And the reason for this, I think, is evident from the sea of electrons model. Again, the metal is being deformed, and that still allows, the sea of electrons model still allows the metallic bonding to continue. Now, if you thought about trying to do that, just for instance, with a crystal of sodium chloride, if you banged on a crystal of sodium chloride with a hammer, what do you think would happen? It'll smash. It will break. It won't flatten out. It will just break because there's strong bonding within the crystal, and it's directional. Okay, later on in chapter 12, depending on how far we make it through, we can talk about why the difference.